Welcome to the fourth video lecture in our fourth class time set of instructional videos. We ended last time with a crude molecular orbital diagram for ethylene, and we discovered that the important part of that diagram consisted of a highest in energy occupied molecular orbital and a lowest in energy unoccupied molecular orbital. We already kind of know what those molecular orbitals look like because we saw them when we constructed a molecular orbital diagram for carbon monoxide in terms of pi-type molecular orbitals and pi antibonding molecular orbitals. But let's ask the question, what does the pi antibonding carbon-carbon molecular orbital look like? Well, the pi antibonding carbon-carbon molecular orbital has a node in the plane of the page, as ethylene is drawn, with two hydrogens coming out of the plane of the page with wedge bonds, and then two hydrogens going back behind the plane of the page with dash bonds. This means that the p orbitals that form both the pi molecular orbital and the pi antibonding molecular orbital will be in the plane of the page. And so for the pi antibonding molecular orbital, the phase of the lobe on one side of the plane of the molecule will be opposite the phase of the other p orbital lobe, and that means they cannot overlap, so there will be a node in the plane of the page. How about the pi bonding molecular orbital? What does that look like? Well, that looks like the lobes of the two p orbitals are the same phase on the same side of the plane formed by the molecule. So the two lobes above the plane of the molecule will have the same phase, which means they can overlap. So really it's not that they're isolated p orbitals because the carbon atom is bonded very close to the other carbon atom. These lobes overlap and bleed into each other, and so the bonding molecular orbital, you can't tell where one lobe begins and the other ends. It kind of looks like a sandwich, sandwiching the plane of the molecule, and that is our second bond, our double bond for the ethylene molecule. That's what it looks like. Because the two lobes of each 2p orbital overlap, there is a higher energy barrier to rotate around a carbon-carbon double bond. So what do I mean? I mean, if we were to rotate around this carbon-carbon double bond, what happens to these 2p orbitals as we start that rotation process? Let's say we rotate a full 180 degrees. Well, what happens to HA prime and HB prime? If we rotate 180 degrees, well, HA prime has now got the dash bond, so back behind the plane of the page, whereas HB prime, which had been back behind the plane of the page, has now got a wedge bond. Well, what happened to our p orbitals? The light lobe is now pointing straight down and the dark lobe is pointing straight up. Well, we just turned our pi bonding molecular orbital to a pi antibonding molecular orbital. So to rotate around a double bond, you have to break the double bond, and that presents a high energy barrier. It can be done at high temperatures. You can isomerize geometries of alkenes, but not at room temperature easily. How about a carbon-carbon single bond? And we'll be talking about rotations and conformations of molecules very soon. Well, it's much easier to rotate around an sp3 bond, a carbon-carbon single bond, because of the symmetry of that carbon-carbon single bond. It doesn't change through the process of rotation. So here we go with ethane. We can go ahead and rotate 120 degrees around that carbon-carbon single bond. So HC is now where HA used to be. HA is in the plane where HB used to be, and HB is where HC used to be. So that isn't hard. Why? Why is that not hard? Because our carbon-carbon single bond our sigma carbon-carbon molecular orbital, it's cylindrically symmetric, so it doesn't matter if you rotate around it, you're not going to be having to break any bonds in that rotational process. So I thought I would finish this video today working an example of trying to generate a crude molecular orbital diagram, perhaps one for formaldehyde, since it's sort of similar to ethylene, but it has another twist because there are lone pairs of electrons, non-bonding pairs on oxygen. So how about a crude molecular orbital diagram for formaldehyde? Here we've got our carbon double bonded to the oxygen. What's the hybridization on carbon? It's trigonal planar, so our knee-jerk reaction should be, oh, that's an sp2 hybridization. And then what are the number and types of bonds? Well, we've got two carbon-hydrogen single bonds. We have a carbon-hydrogen or a carbon-oxygen single bond, and then a carbon-oxygen pi bond, and then we have these two lone pairs on oxygen. How are we going to construct our molecular orbital diagram? Well, we'll start with the two carbon-hydrogen single bonds. We know that means we have two sigma carbon-hydrogen molecular orbitals. And if we have two sigma carbon-hydrogen molecular orbitals, we have two sigma star antibonding carbon-hydrogen molecular orbitals. We have a carbon-oxygen single type bond, a sigma CO. And if we have a sigma CO, we must have a sigma star antibonding carbon-oxygen molecular orbital. We know we've got a double bond, so that means we've got a pi CO molecular orbital, and if we have a pi CO, we'll have a pi star CO molecular orbital. So what do we do with the lone pairs on oxygen? Well, they don't participate in bonding, and we throw non-bonding lone pairs or empty atomic orbitals between the antibonding and bonding molecular orbitals in terms of their energy. So for this molecule, we have to put two non-bonding atomic orbitals, they're sp2 hybrids actually, on oxygen, that each accommodate two electrons between the antibonding, the pi star CO, and the pi CO. So what does that mean in terms of formaldehyde's highest occupied molecular orbital and lowest unoccupied molecular orbital? Well, the lowest unoccupied molecular orbital is the pi star CO, and that's the orbital that can take electrons, and when it does, it usually has the effect of breaking the pi bond. What is the highest occupied molecular orbital in formaldehyde? Well, it's those non-bonding electron pairs on the oxygen. So if formaldehyde is wandering around and wants to donate its electrons to another molecule, it will donate the highest energy ones, and they will be the non-bonding pairs of electrons on oxygen. So I hope this exercise was useful. We'll, like I said, work some other exercise problems during the class time, and hopefully you'll have a more stronger feeling for this type of material. And in the next class time, I think we'll move on towards bond line structures and naming. So goodbye until then.